Welcome everybody. In this presentation, we will going to show the progress in terms of workflow improvement of existing modules and implementation of new ones in Iber. The development and improvements of Iber are the result of the effort of the Water and Environment Engineering Group of the University of A Coruña, the Flumen Institute of the Polytechnic University of Catalonia, and the International Center of Numerical Methods in Engineering, also in collaboration with CEDEX of the Ministerio de Fomento of Spain. What's Iber? Iber is a two-dimensional software for the simulation of free surface flow, transport processes, morphodynamics, and eco-hydraulics in shallow water. Since the beginning, new functionalities have been implemented. These have served to make Iber a useful and applicable tool for professionals in civil, hydraulic, agricultural, sanitary, marine, and oceanographic engineering. Since 2010, the Iber and GiD team have evolved this tool to make it more simple, improving the workflow and making it more user-friendly. In a simple way, we can differentiate three levels when building a model in Iber: pre-process, calculation, and result post-process. Throughout this presentation, the improvements will be presented in this order. First of all, in the pre-process, one of the latest implementations was to include a new toolbar that looks for simplifying all of the workflow. The user has shortcuts to functions such as load background image, show or hide the background image, generate the mesh in the established conditions, load the topography, launch or cancel the calculation, and see the general information of the model or the Iber version information. Additionally, a function that allows the user to modify the topography manually is also included. CEDEX has developed a specific program that allows to transform LiDAR files to digital terrain models. This tool has been implemented into Iber because it can be very useful to work with this kind of topographical data. Iber is able to simulate hydrological processes. The way to implement rain events has been improved by giving a specific location of one or more rain gauges, so that the assignment of each element will be made based on the distance of the element in question from the rain gauge. Iber can also work without considering the gauge location, but when it is assigned, the manual allocation prevailing over automatic. The implementation of the rain losses due to infiltration processes has been improved considerably by adding two automatic allocation methods. The first, using a raster file per parameter, suitable for the detailed spatial variations of each parameter. The second automatic method involves the generation of infiltration zones. The infiltration of the elements assigned to each zone is calculated using the parameters defined in the corresponding zone. To assign each zone, a raster must be loaded that assigns each element the ID of a zone. The groundwater flow module is one of the developed novelties. Based on the available data of the subbasin, the calculation of the groundwater flow can be incorporated by two methods. The first is a simple distributed model where the defined parameters are made part of the infiltrated water trickle into the deeper aquifers, and the rest of the water is filtered in the main channels. The second method consists in a lumped model that requires more effort and knowledge for its correct use. Subcatchments are defined and assigned to both the infiltration reservoir zone and the exfiltration zone, leaving at the discretion of the user the correlation between capture and exfiltration. Another new model implemented is the soil water stress, which is appropriate for long simulations and domains where agricultural land use predominates. The water necessities of the crop type have an important effect on evapotranspiration process. This model is implemented for manually assigned surface by surface or element by element of the crop properties. The control of the activation of each module referring to hydrology is carried out through the corresponding tab in the problem data. In this way, despite having assigned various types of infiltration or groundwater flow models, you can easily control what should be taken into account when launching the calculation. This tab would be the control center of the hydrological processes in Iber. Now a new module implemented allows the user to simulate soil erosion processes. It works as the infiltration losses by zones, creating areas susceptible to erosion and constituted by certain number of types of sediment. These zones are assigned by a raster that associates the zone ID to the elements. Like the Hydrology tab, a non-tab controls the soil erosion module. Here the user can modify the properties of each sediment class and establish the complexity of the model based on the information available and the results needed as outputs. New pollutants have been implemented in the water quality module, such as phosphorus, phytoplankton, pH, metals. Likewise, a new menu has been created to spatially introduce the most significant atmospheric variables. The control tab of the water quality module has been restructured and simplified to make its use more agile and simple. Now the mixing parameters and calculation scheme has been unified for all pollutants. The urban drainage is an existing model that was not fully developed, and some parts had to be written manually. This model allows to simulate the dual flow, surface sewer, considering free surface flow or pressure flow in the sewer. The existing version has been restructured, adding new tools, windows, and processes to simplify the whole build-up process by including the sewer network from GIS files. The problem data tab has also been restructured to make it more user-friendly and providing additional options to carry out more complex simulations, as for example the consideration of sediment transport processes in the sewer network. In 2018, Iber is also able to work as eco-hydraulic tool, including hydrobiological aspect of fishes. This module allows to simulate the weighted usable area for fishes, which is a parameter for the assessment of the ecological state of rivers. Since that time, few improvements have been carried out, such as the automatic assessment of weighted usable area. Future works will develop this model, including, for example, different kinds of species, more variables, and eco-hydraulic criteria. For the third level of the workflow, if you remember, result analysis has also been simplified to make it more user-friendly. Just like in the pre-processing part, direct access buttons have been added to functions such as showing or hiding element labels, creating profiles and representing certain values of elevation of the free surface, exporting result to raster, etc. There are other improvements in development. For example, the new criteria for assessing the floodplain encroachment based on hydraulic aspects. This new tool can improve the whole process that currently needs a tedious iterative process, reducing the number of iterations at minimum. Finally, the Iber team wants to say thanks to the GiD team, because Iber is the perfect example of collaboration between both. For those who want to explore Iber as the multidisciplinary tool that it is, you have information about the program at www.iberaula.com, and also you can download it for free. Again, thank you all for your attention.